The asteroid belt, the gateway to the outer planets. On a distant cosmic morning about 4.5 billion years ago, when our solar system was little more than a screaming newborn in the infinity of space, something went wrong between Mars and Jupiter. Where a planet should have formed, a sort of big brother to Earth, we instead find thousands of cosmic rocks wandering in an orbital limbo, the main asteroid belt. If we could fly over this region aboard a spacecraft, we'd enjoy a view that would defy imagination. Rocks of all sizes, from as small as a pebble to as large as a mountain, silently orbiting in the void. Actually, no, scratch that. Truth is, we wouldn't see much of anything unless we had the luck, or bad luck, of getting close to a really large asteroid. Otherwise, just stars, darkness, and a few moving points of light. You're probably wondering what astronomical knowledge those sci-fi movies base their fantastical scenes on when they show the asteroid belt as some kind of cosmic obstacle course. Well, you'll get the answer from this video. The main asteroid belt occupies an apparently privileged region of the solar system. Where is the asteroid belt located? Extending roughly from 2.2 to 3.2 astronomical units, AU, from the Sun, where 1 AU corresponds to the average Earth-Sun distance, about 93 million miles. In more concrete terms, this belt is nestled between the orbits of Mars, $1.524 Australian dollars, and Jupiter, $5 Australian dollars and 20 cents, serving as a natural boundary between the inner rocky planets and the outer gas giants. But how crowded is this region? The numbers are simply mind-boggling. We currently know over 1.1 million asteroids in the main belt, but the estimated total number of objects with a diameter greater than 0.6 miles, 1 kilometer, exceeds 1.5 million. If we include smaller bodies, we easily reach tens of millions of objects. Yet, despite this apparent congestion, if a hypothetical spacecraft were to cross the belt, the chances of accidentally colliding with an asteroid would be extraordinarily low. The total mass of all these objects, about 4% of the Moon's mass, or roughly 3 times 10 to the power of 21 kg. An impressive number when we think of individual objects, but surprisingly modest on a planetary scale. It's as if all the material destined to form a planet was scattered in a cosmic explosion, leaving only fragments of what could have been. How did the asteroid belt form? Theories on formation. How did the asteroid belt form? Why do we find millions of rocky fragments in that region instead of a planet? This question has been haunting astronomers for at least 2 centuries, and over time various theories have emerged, some now abandoned, others still the subject of heated scientific debate. The oldest theory, now discarded, suggested that the belt resulted from the explosion of a hypothetical planet that once orbited between Mars and Jupiter. This idea, popular until the mid-20th century, didn't hold up to the facts, mainly because analyses of meteorites that reached Earth, which are nothing but fragments of asteroids that managed to reach the ground, showed that the material they're made of never experienced the pressures and temperatures that exist inside a planet. Today, scientists think that asteroids are the result of a planetary miscarriage. That is, they're planetesimals that couldn't form a planet in this area due to Jupiter's gravitational disturbance, which was capable of perturbing their orbits and shuffling them to the point of generating several collision routes between these small bodies. The mutual impacts would have fragmented the planetesimals into smaller and more numerous bodies until the current situation, where impacts have drastically decreased, but not before dispersing much of the material originally present in the region by ejecting it toward the inner or outer solar system. Computer simulations indeed show that the mass of the asteroid belt could have originally been 1,000 to 2,000 times greater than its current mass, sufficient to form an Earth-sized planet. Jupiter's action would have removed 99.9% of this material, leaving only the fragments we observe today. The hypothesis about Jupiter's preponderant gravitational influence seems confirmed by the presence of groupings of true asteroid families, evidently formed by fragments derived from those ancient collisions, and by the confirmed existence of orbits, the so-called Kirkwood gaps, named after the astronomer who identified them in 1866, completely empty of asteroids and others where, on the contrary, asteroids seem to be piled up in large numbers. In short, we can certainly say that the distribution of asteroids in the main belt is not uniform, but structured like Saturn's rings or the grooves of a vinyl record. Hey guys, just a moment before we continue. Be sure to join our channel The Science Signal. Click on the bell. You will help us to make products of ever higher quality. The Lords of the Belt. In this vast collection of space debris, some objects stand out for their considerable size. The undisputed giant is Ceres, with a diameter of about 585 miles, 940 kilometers, so large that it earned the title of dwarf planet in 2006, the same category as Pluto. Ceres alone represents about a third of the total mass of the main belt. Discovered on the first day of the 19th century, January 1, 1801, by Italian astronomer Giuseppe Piazzi, who initially classified it as a comet and then as a planet, this celestial body was the first asteroid ever identified. With a diameter of about 585 miles, 940 kilometers, more than a quarter of the Moon's diameter, Ceres is so imposing that it alone contains about a third of the total mass of the main belt. Its internal structure is surprisingly complex for a simple asteroid. Studies suggest it's differentiated into layers, a rocky core surrounded by a mantle rich in water ice. Observations from the Dawn probe revealed a surface rich in hydrated minerals, particularly phyllosilicates, clays, and carbonates, suggesting intense aqueous activity in the past. From a geological standpoint, Ceres's surface features a variety of characteristics. Impact craters of various sizes, isolated mountains like Ahana Mons, a cryovolcanic dome about 2.5 miles, 4 kilometers, high, vast plains, and complex fracture systems. The relatively young age of some of these formations suggests that geological processes on Ceres continued until recent times, contrary to what one would expect from a small celestial body that should cool and solidify rapidly. One of the most enigmatic features of Ceres are the mysterious bright spots observed at the bottom of a Cater crater. These patches, extremely reflective compared to the rest of the dark surface, are primarily composed of sodium carbonate and other salts. Scientists believe they formed when salty liquid water emerged from inside the asteroid through fractures, then evaporated, leaving salt deposits. Even more surprising is the probable presence of an underground ocean of liquid water, or at least layers of brine, salt water, beneath the crust. The Dawn probe also detected evidence of recent cryovolcanic activity, eruptions of ice water and mud instead of lava, indicating that Ceres is geologically active. Its complexity led the International Astronomical Union to reclassify Ceres as a dwarf planet in 2006, the same category as Pluto. It is the only dwarf planet located in the inner solar system, a true miniature world that challenges our conceptions of the boundaries between asteroids and planets. In second place among the giants of the belt is Vesta, with its diameter of 326 miles, 525 kilometers. The Lords of the Belt 2. Vesta 3. Pallas. Vesta is considered a survivor. Its surface bears the scars of a catastrophic collision that tore away much of its southern hemisphere, generating a family of asteroids that share the same chemical composition. Completing the podium is Pallas, 318 miles per 512 kilometers, which has a diameter comparable to Vesta's, but is much less massive. It's curious to note that, despite their impressive dimensions, these objects maintain irregular shapes. Only Ceres has sufficient mass to assume a spherical shape under the effect of its own gravity, one of the fundamental requirements for classification as a dwarf planet. Rocks of all types. If you think asteroids are simply gray, anonymous rocks, prepare to be surprised. The main belt is a veritable mineralogical showcase, with asteroids of surprisingly different compositions. Astronomers have developed a classification system based on spectral properties, which reflect the surface composition of these bodies. C-type, carbonaceous, asteroids are the most common, representing about 75% of known asteroids. Dark, rich in carbon compounds and hydrated minerals, these primitive objects preserve material almost unaltered from the early days of the solar system. They're like time capsules that allow us to travel back billions of years. S-type, silicaceous, asteroids constitute about 17% of the population and are composed mainly of iron and magnesium silicates. Brighter and more reflective than their carbonaceous cousins, they dominate the inner regions of the belt. Many of the meteorites that fall to Earth come from this group. M-type, metallic, asteroids are relatively rare, representing only about 5% of the population. As the name suggests, they're rich in metals, mainly iron and nickel. Many of them are believed to be exposed nuclei of ancient differentiated planetesimals, whose outer layers were stripped away by cosmic collisions. In simple terms, they're potentially precious metal space mines floating in the void. There are also rarer types, such as V-type asteroids, associated with Vesta, D, E, P, and others, each with unique characteristics that tell different stories about the origin and evolution of our solar system. The orbits. Speaking of the asteroid belt as a single uniform ring would be an oversimplification. Asteroid orbits form an intricate tapestry of ellipses with different eccentricities and inclinations relative to the ecliptic plane. Most asteroids follow relatively elliptical orbits, where the statistical distribution shows average eccentricity values of 0.145 for the inner belt, 0.143 for the middle belt, and 0.126 for the outer belt. All values about 10 times higher than that of, for example, Earth's orbital eccentricity, which is 0.0167. However, there are numerous exceptions to this rule. Some asteroids follow very eccentric orbits that cause them to vary considerably in distance from the Sun during their year. Others have high orbital inclinations, traveling well above or below the ecliptic plane. These orbital varieties are often the result of ancient collisions or gravitational perturbations accumulated over billions of years. Close-up explorations. Until the 1990s, asteroids had been studied exclusively from Earth, appearing as simple points of light in telescopes. The situation changed radically with the advent of space exploration via probes. The first spacecraft to cross the asteroid belt was Pioneer 10, which entered the region on July 16, 1972. At the time, scientists feared that debris in the belt could pose a serious risk to the spacecraft. These fears proved unfounded. Since then, 11 spacecraft launched from Earth have crossed the belt without any incident. The density of material in the belt is so low that today it's estimated that, for a probe, the chances of colliding with an asteroid are less than 1 in a billion. Early missions like Pioneer 11, Voyager 1 and 2, and Ulysses crossed the belt without taking images of asteroids. It was the Galileo probe, during its journey to Jupiter, that captured the first close-up images of asteroid Gaspra in 1991 and its small moon Ida in 1993, revealing for the first time the true face of these rocky worlds. In 1996, the Near-Shoemaker probe, after flying by asteroid Mathilde in 1997, actually landed on asteroid Eros in 2001, determining its density with extreme precision from measurements of the gravitational field. Most images of belt asteroids come from these brief flybys of probes headed for other targets. Only a few missions have had the primary objective of prolonged study of the asteroids themselves. NASA's Dawn mission represented a real turning point, becoming the first probe to orbit 2 distinct bodies in the solar system. Launched in 2007, Dawn explored Vesta from July 2011 to September 2012, then moved to Ceres, where it remained in orbit from 2015 until the end of the mission in 2018. The Japanese space agency JAXA's Hayabusa mission accomplished an even more daring feat in 2005. Not only did it visit asteroid Itokawa, but it managed to collect samples from its surface and return them to Earth in 2010, despite numerous technical difficulties. The success was replicated with Hayabusa 2, which collected samples from asteroid Ryugu and returned them to our planet in December 2020. NASA was not to be outdone with the OSIRIS-RX mission, which collected samples from asteroid Bennu, returning them to Earth in September 2023. These samples, the first returned from a carbonaceous asteroid, are revealing valuable information about the primordial composition of the solar system and the possible ingredients that led to life on Earth. Conclusion. This rocky belt represents an invaluable cosmic archive, a stone library that tells the early chapters of the solar system's formation. Each asteroid is a silent witness to a primordial era, preserving clues that would otherwise be lost. As we continue exploring these ancestral fragments, we're not just studying space rocks. We're reading our own cosmic history, understanding the events that allowed, billions of years ago, the birth of that small blue planet we call home.